you back to the next session of embedded software testing Unit 2 series, where we study about the testing methods. Today's session we will touch on the model based testing and its technique and the details. Before that, we will in the last session we had gone through the state or event transition and testing. So today's session we will continue that, because the last session is important in terms of state transitioning, and the model based design and development and testing is based on the states, state machines, grammars and all that. So what we studied last time is the state transition technique, in which we studied about composing the states, composing the transitions tree, and test script legal cases, test script illegal test cases. It is something like robustness. Illegal means it's not that unethical or something like that. It is beyond the normal test cases, so called as illegal test cases, and the script cards, which is optional. Okay. So other thing is we took an example of a cassette recorder or a video cassette recorder, which has about 5 states: standby, play, record, fast forward, rewind. And as far as the practicality is concerned, we studied about all the transitioning gods, conditions, and the events that are going to happen between these. And accordingly, we know that there are a number of arrows for all of these. So we listed out a state event table, which identifies about 18 types of state events, and the dotted ones are cannot be achieved, which are illegal, but the system should not accept. So the tester should try to do these dotted ones as a robustness, but the system should not accept as a state event. That is why these are all dotted, and it's called as illegal combinations. And different events are standby. Different states are standby, rewind, play, fast forward, and record. Also, we had drawn a tree which talks about the path, which is nothing but the control path. I will again rewrite so that the very important term in embedded system, control path. There is also something called as a data path, which we don't need to control coupling, data coupling. Very important term it is being used in embedded system. So for now, let's focus on control coupling or control path, which is nothing but the execution of the program, taking or considering the different events that are happening within this system events. So that is nothing but the transition tree. So we have about 14 test paths starting from standby, and its substate is rewind, its substate is play, fast forward, standby, and standby. Like this, play also have. So all these combinations. We have seen the different paths that are taken up in the state event transition tree, where we have the primary event as a standby, then we have rewind, play, fast forward, record, etc. So all these paths have to be tested. Then we have drawn a table or a state chart table for the VCR, having identified with identification legal 1.1, 1.2, 1.3, 2.1, 2.2, 2.3, etc. All these are basically event based. So there is the input and the condition, the next one, and the expected result. So this is how this needs to be done in terms of state transition testing. Continuation of that. So we have illegal test cases also. What we have seen is the dotted ones having identified as I1, I2, I3 till I16. The setup for this will be similar to the whatever legal ones we have, where we need L1.1 setup. That means rewind state is required, and rewind to event rewind we need to move, which is an illegal script basically. Similarly, all these are have been listed out. So there are practical issues which we have seen. Hierarchical state charts, to draw it, it may be a little challenging. You need to have a practical knowledge as well as the system knowledge. Requirements of course will help as well. Then coverage, extensiveness, we need to have it. So state charts are very important in doing this. Then detecting the fault, practicality and feasibility in achieving all this. So these are some of the practical issues in state transition testing. So that needs to be handled very meticulously. There is another term called mainstream usage testing, which talks about we should not stuck ourselves into boundary cases only. We should also see some of the good values as well in terms of a normal input as well as normal expected output. So typically that will be used when the system is running. That's how we do it. Okay. So model based testing and design we will see today. I will go back to that slide which we were seeing it. I think yeah. Okay. So before model based testing, the models have been developed in the development phase with the help of a model based design and development such as MATLAB or Simulink. There are of course different tools also, Verilog, VHDL, etc. Those are specifically for the hardware. For complex systems, we use model based development and testing. Basically, it uses the different models for the system under the development or test. Those models are nothing but different diagrams, charts. So those will be done. Once we have those models, and those models with the help of the tool can be used to generate the code, and that code can be deployed onto the target. Basically, that code can be generated in the host and can be deployed onto the target, and the target can be verified with the help of the target based execution. But before that, we may have to do some tweaking. It is not 100% what is it called directly usable with the help of auto code generated code. So that we need to little modify the auto generated code. Similarly, for verifying it, we use the same modeling concept for testing. That means basically this model is a framework for us to go for the testing, which is nothing but the model based testing. We will study that later. Before that, I just want to describe in brief about model based design. So philosophically, there are a lot of tools. Conceptual wise, we have a UML, Unified Modeling Language. Then we have SysML, System Modeling Language. So these are basically dealing with all the use of transition diagrams, state charts, all these type of what is it called representing the system in terms of how it executes, how it is getting modeled. So that is how these are all very useful. Once they do the models, they then generate the code, and with the help of the target, they will add additional code in terms of wrapping the generated code into the target. Then they execute it. Same philosophy we use for testing also. The same model concept is being used. So that is how it is called as model based testing. So let us see about model based testing in the next slide. Okay. So basically, model based testing is a process of test generation from the models. as I explained in the previous slide, for the system under test. There are a number of methods that can be applied for MBT. MBT is nothing but model based testing. The test cases are created automatically using models instead of manually. That means we have created the models, and the tests are being generated automatically with the help of this model. Okay. Test cases are created automatically, as I said. The same test cases with the help of test hooks, we will generate the script and execute on the target board. The target board is already having the modeled code which is executing on the target. So basically, three classes are getting identified: model, test generation, and test execution. These are basically the classes they say about MBT, model based testing. Okay, so definition, let's see what is model based testing going by the Wikipedia. Although there are several definitions, most of them carry the same basic idea about an model describing a system and a system of some sort, and some way of using that model to get the test cases or generate the test cases. Basically, it is called as test sequences. Test sequences or test cases are derived from the model. So that is the fundamental about this. So model based testing is a software testing in which test cases are derived in whole or in part. That can be completely for submodule model, or smallest of the model, or as an entire model where we have top down, as I said in one of my earlier class, or bottom up. Any of the approach where we consider the smallest of the units and go towards upper side, something like an integration approach as a bottom up, so we can use. Otherwise, top down, where we have the high level requirements, definition is very clear, and we have the models, we can use the top down approach in terms of holistic testing. So model based testing is software testing in which test cases are derived in whole or in part from a model that describes some usually functional aspects of the system under test. That means the model basically defines and describes the functional aspects. So each model has its own functionality, features, inputs, outputs, what are the signals. Signals could be analog, discrete, whatever it is. So all this will be part of the functions which are basically used to describe the model. So all these are useful in terms of developing the test. That can be as a whole as well as a unit. So that is the definition of model based testing. Okay. Let's see some of the advantages of model based testing. As I said in one of the thing, it is very useful for complex systems. What are other advantages that model based testing has? Let us see. Model based testing is very easy to understand because the model is visible. That means the user can see the pictorial representation as well as the complete representation of each of the submodules that it comprises. So basically, it is very easy for a tester, a developer, or from the customer perspective. So basically, complex systems can afford to have some time spending on developing the model in advance. So they use this model based development in testing. So this is useful because it's easy to understand from all the perspective, designer as well as the tester, primarily the developer and then the tester. Model based testing separates logic from the testing code. That means we don't have to have a code uh, at the individual level. We can have the logic at the business level. That means the functionality as a whole and the functionality as an individual level both can be segregated separately, and the code that we have which we want to test it, that can be separated out. So it will be very easier segregation of the different levels. So easier segregation and integration. So this is a basic thing that will help in terms of separating it. So that is the advantage. Model based testing increases the test coverage with the same effort as classic test automation. So classic test automation, we don't have a models or model based testing. We basically go by the requirements, and the requirement pertaining to that we will try to understand the functionality and try to feed the signals and all that. So where the visibility is much uh, unclear. That means especially complex systems. So very useful where we have a complex systems to have model based design and testing. So in terms of classic test automation, the coverage is somewhat difficult. It is called coverage control. That means uh, we need to spend a lot of effort in terms of having the coverage and understanding the coverage and reporting the same. But whereas the model will basically help which models are done, what are the signals covered. So basically, it's a concrete idea it gives for the coverage purpose. Okay, model based testing is the fastest way to get use of automated test. That means somebody to have understanding and develop the automation, it will be easier to have a model available for testing. So that is the meaning of the last advantage. Okay. So the other advantages are something like uh, though the models not have been implemented completely, there are design and other things that could have been done already, but without the need of the implementation, somebody can start the test cases or test scenarios definition. That means the earlier verification is very easy. That means by seeing the models, we can find the test flaws. That means a tester can find some of the issues that the model has by visualizing it and going through the model itself, having his own sort of test cases identified. So that is the advantage. Then verification simulated using tests based on high level requirements. That means verification can be simulated. We don't need to have a target actually. We can do offline as it is told in the next one. The tests can be accomplished on the PC instead of the target. We don't need to have a target based systems in the beginning. We can have the verification done using simulation of the models for the high level requirements. We can basically have a coverage from the high level requirements to the models that we have under test. Model based testing enables us to switch testing tool if needed or support multiple platforms using the same model. That means if the model supports the platform that is being deployed, same thing can be used for testing also, and the tools that are used is very easy to switch. That means the same models which are developed and deployed onto the target with the help of the tools can be used for testing also. So that is the advantage of that. Okay. So the next one is model based testing focuses on requirement coverage, not how many test cases you have executed last week, etc. That means you don't have to care about the schedule and all that. Of course, that's a different aspect. but we go by model, and each model we cover as you progress and focus on the model. You automatically going to cover the more requirements automatically. So that's the advantage. Last one being model based testing proved to positively affect the maintenance problem, nemesis of all test automation. That means the maintenance of the models as well as the model based testing is easier compared to uh, the requirement based testing of without the model. What we have, what we can say as classic automation testing, because models once it changes, it's easier to adopt the testing changes as well. So that is why model based testing is easier to maintain compared to the classic automation testing. Okay, we will take an example. This is again a reference from one of the uh, good example from the web actually. A model describes how a system should behave. We can understand with an example below. So we need to supply the action and see if the system responds as what you expect. That means we have a states defined as a blocks. You can see there are the 4 blocks below, right? So we take this as an example where we have notepad. Notepad as an example here. You can see we all know that how we operate the notepad. We have notepad executable opened. We are going to start. So there is a blank notepad that is going to open. If you don't want, you can close it. So the operations that can happen in this model is that start and close. The next what we are going to do once we have started the model is that we are going to type something, and if you don't want to type that, we are going to delete it. It will be back to the blank sheet, and once we are done, we are going to close it. Once we have typed it, we are going to close it. While closing, it will ask whether to save it or not save it or cancel it. So cancel means it will be back to the same state what which is having it. So that means the third state or the action will be done with the help of this transition, and we don't want to save. It will be back to the notepad execution mode where the notepad is closed. So a simplistic approach. Here we can see the model is described this way. So the model should work something like notepad as an executable, should open, should be able to type, should be able to close and cancel, and no operations should be there. So we know what are the actions that system, the notepad system can respond as a model when we try to subject under test, because this has already been developed. So that is the fundamental about model based testing. Okay, so once we understood about the model based example with this notepad, we will try to understand what are the tasks of MBT, model based testing. So there are about 6 steps or 6 tasks: understanding the system, choosing the model, building the model, generating the tests, running the tests, result collection and reporting. The typical system testing what we have seen in the unit 1 classes. So similar things will apply here also, where we do the model based testing. First we need to understand the system. Here system means the models. So we need to understand the model first. Once we understood the model, we are going to start the test by choosing the right model. That means which you want to test, which you want to target first before we attack the submodels or submodels in terms of the top-down approach. So all the selection criteria will be done the help of choosing the model this step. Once we have this, we do the build the model. That means we develop the test model what we want to do it. Once we have that model that is ready for testing, we generate the tests. That means all scripts for this model can be done, or we will do a run through of this model with the help of various tools such as UML and all that. Then once we identify the tests, we want to run it to see that how the model behaves. Once we are executed the tests or run the tests, we have the result collection and reporting in terms of coverage and all that. Okay. Understanding the system, basically forming a representation of the system's functionality. Let's say prerequisite of building the models. This is a small task basically, because already we have the model and the complexity will be self-explanatory in terms of understanding it. So basically the software whatever is being developed for that particular model will be deployed onto the target. So all this information will be part of that model. By understanding the model, we know that what the model does. So basically we determine the components, features, what are need to be tested. That is the objective of that particular test. So while doing the understanding of the models, so we also have to establish a sort of a communication called communication with the requirement. With requirements, design, development team, whatever it is, that is very important, because we need to establish the model mapped with these aspects. So it's very important. Along with that, we are going to identify the users who are all there, so how we can interact. So we'll also identify the inputs. Inputs, outputs, how it can be driven, all these aspects will be studied. Domain study is called basically. There will be number of documents that we need to understand to map what we have understood the model basically. So based on that we will write the tests. That is why it is very important to have a understanding the system. Next we have choosing the model. So basically what we do is we select which model, how we can test it. That means this basically help in terms of grouping, because there are a number of models. We need to understand what are the models which can be grouped, so that can be tested or attacked in terms of testing it. So that is why choosing the model is very important. So then we have the procedure for building the model. This is also a very important step. So where we will basically build. That means we put the constraints, inputs, outputs, all this will be laid out in doing the building of the model. And of course behavior and behavioral constraints also important. So these are some of the building the model aspects that needs to be taken care for doing the model based testing. Next we are going to have the generating the tests. So something like we have a finite state machines or state diagrams. So we need to traverse. We have seen how those paths can be done and what are the sequences. So there are different state charts, state diagrams, sequence diagrams, activity diagrams. So many are there. Maybe when we have a class for the UML, we will study all of this. That is all aspects of model-based design and development. Those things needs to be done in terms of the generating tests, because having understood that events and sequences, we can have the tests where to trigger and all that. Then once we have that, we are going to execute with the help of a script which can help in terms of executing those tests, providing the inputs, running the conditions, and providing the outputs also. So those are some of the running the tests. Once we have run the tests, we need to evaluate it, whether tests are correct. So it is very important to understand how it has passed, similar to fail, why it has. So very important points. Pass doesn't mean that it should be passed. It could have been passed wrongly, or it could have been erroneously passed. So how do we evaluate that? So that is also very important. So we need to evaluate our pass and fail criteria while doing the model-based testing. So those are the tasks that we have for the model-based testing. We'll take one reference that I got from the web. Examples of model-based testing, where and all they use. So you can see there are the finite state machines, FSMs it's called, which has different states. Example here is been given as two states, two events basically. One is a door open, second one is a door close. The first state is open the door, second is the close the door. So there is the action, open door. From closed state it will move to the open state. Similarly, from the open state it will go to the closed state with the help of closed door action. So this arrow is a transition condition. Similarly, we use the state charts which we have seen, entry, and there is a content, there is a link. So and what are the entry state it has in terms of various actions. So there is an author, created, modified, etc. So there are a lot of aspects that is involved in terms of this is called a class diagram. This is done with the help of UML, Unified Modeling Language. It's one of the very popular to represent the models or use the models. And we have other models, model-based software testing also. That is called the Markov chains, grammars, which are a bit complex in terms of understanding testing. We need to adopt any one of these models and go in detail and deep. That will help in terms of model-based testing. So these are examples of models that can be used. It can be FSM, state charts, UML, Markov chains, grammars, any of those. So we'll take a simple model which we have studied. We start with how we can start with the test. A simplistic approach is that very simple is that you identify two states. Very simple. Like first one is the not running, next one is the running. So the model can be entered with a running state, the model can be exited with not running state. So we will start that way. So that will help in terms of understanding the complexity when we go in deep. So not running and running, start will go for running, stop will go into not running state. So these two are represented as a one model. So how we can do a test is with that we will apply a condition which is good for triggering not running to running. So something like we will set the start as true or start as triggered, that will enter into running. So we will verify that whether the state has changed to running. Similarly, the next test case will be whether it has whether it has changed from running to not running with the help of a stop command. So two test cases we have identified. Similarly, we will see the next level of complexity in the next slide. You can see there are about 4 states. I think this is an example of a calculator. Yes. So what we can do is, so what are the different states that calculator can have? We take that as an example. Not running or a standard state, it is called. We know that it will go to running with the help of a start, and it will go back to not running with the help of a stop. So two test cases can be there. Similarly, for the second one, running standard, it can go further deep as another running state, which is called scientific. We know that calculator can operate. We'll open a calculator. I guess you can see the calculator. So we know that the calculator can run in standard as well as non-standard way. Non-standard could be a scientific, which we can choose with the help of the file edit and select the scientific. So that's how we can do it. Yeah. Here from scientific, it can go to not running scientific. So likewise, we can have a model-based testing where we represent the model in terms of different states and how the model can be triggered into different states. We can understand with the help of a standard example calculator. Going with more complexity, we can see here not running, running, then there is a running standard empty, running standard non-empty, scientific empty, scientific non-empty, etc. So each one has its own sort of a conditions. All this can be executed with the help of the model-based testing, where we apply the different states into considerations. Here you can see one set of this is there, other set of state conditions are existing. Likewise, we can have the complex model-based testing where we have more states. So here we have second one. The next path it could take to 4, or it could next go to 3, then from 5, then it can go to 6. From 6, it can come back to 1. So likewise, we can have. You can see. You can see to it. I'll try to separate it out so it will be easier for you. This is the original model. This is the test model. It's an exact replica of the model. So here we have the model. Here we have the MBT. That is one path where we have tested. So this is looking like same as the original model. So we apply the model-based testing philosophy to apply all these test scenarios into the model, where the model is represented with the help of the left hand side different blocks. So that is the concept of model-based testing. So I'll repeat again. All these model blocks can be tested with the help of different events, where the events can be from not running to running, running to scientific, scientific to scientific empty, scientific non-empty, etc. So all these 5 blocks in this complex example we can have, and each can go into different path with the help of a model based testing approach. So which is represented with the help of a model based testing model, another model which is another replica of the original model you can see on the right hand side. So that can be called as a model based testing. I will delete it so that come back to the original model. Okay. Okay, so there are 3 aspects that we have tested: application status, mode status, display status, which can be many things actually. Going by the example, we can see the application is running or not running, because that is the primary states which was made with the help of a running state from the standby state. In that way, we know what is the status of the application. Similarly, we have a mode that also can be tested. So what are the modes that can be triggered to enter into different status? We can choose standard method or a scientific method. So these are primary inputs for testing the mode status. So test cases are written in such a way. Then we have a display status. The display can have a B, C, or in terms of hexadecimal, in terms of numerical, it can show 0 to 1, 2, 3, 9, whatever the number, and it also can show plus minus the logical operations and or whatever it is. So primarily, the calculator example has three types of statuses against which that calculator model will be tested. So application status, mode status, display status. Application status has running and not running. Mode status has a standard scientific, and display status has empty and non-empty. So right hand side you can see the various steps that are involved: the start, scientific, stop, start, standard, stop, clear, stop, start, scientific, clear. So these are some of the executions that can be done like a test scenario. So there are about 14 test scenarios that have been listed on the right hand side. All this can be applied to test one of these 3 aspects or 3 features of the function. So calculator may be having a requirement something like the calculator application should enter into a running status. Calculator should be able to do not running status, should be able to enter into. So this is one requirement. Requirement 1, requirement 2. So instead of writing calculator should go into running, not running. So it's very easy to have a model what we have seen in the previous example. With the help of that model, we start with a simplistic approach, then little more complex, then the full complex approach, considering the model as a whole. So that is how model based testing is carried out. Okay. On the right hand side you can see the different scenarios have been listed out. Okay. The various what is that called taxonomy of model based testing. This will cover basically all aspects of model based testing. This is the what is that called complete model based testing overview. This is again described in detail in model based testing of real time embedded systems in the automotive domain by Justina Zander Novica. There is a book called Model Based Testing for an Automotive Domain. So that has a more depth, clear description about model based testing. where he has basically uh, have a categorization in terms of classes and categories and options. You can see the first column having the classes, model, test generation, test execution, test evaluation. So these are some of the classes that are used for model based testing. Then we have categories. Model itself is a category where we draw the model. Next one is a test generation, where we have a test selection criteria. We know that test selection criteria can be uh, based on the black box approach, having events or the various dynamic testing that we have seen in our earlier classes. And that test selection criteria can be applied with the help of this options column. That test selection can be structural model coverage, data coverage, requirements coverage, test case specification, random, and stochastic, fault based. So all these are type of options that can be used for test selections. So with the help of that, we are going to have a test generation for this model, for this class. Test generation is another class. Then we have the technology. What sort of a technology we are going to adopt for this test selection criteria? As I said in my earlier slides, it could be automatic or manual, a black box or white box. Then random generation, graph search algorithms, model checking, symbolic execution, theorem proving or algorithm proving, online or offline. There are a number of things, number of options that can be used in terms of the tools or technology. Next, we have identified this test generation as a class. We go for execution class. How we are going to execute. So execution options are model in loop, software in loop, hardware in loop, etc. So it could be reactive as well as non-reactive. So we are going to observe in terms of non-reactive mode. In terms of reactive, we are going to inject it. So that is one class. The next class of the model-based testing is test evaluation. Test evaluation has basically specification in technology. The specification will refer uh, in mapping the tests that we have done with the above test execution after we have the test generation as another class. So what it helps is we refer all the features, functionalities that have been tested or test executed, and all the signals, whether that is covered, robustness, normal, boundary, etc. All these test selection criteria and the execution options will be specified. And also that specification will have a coverage in terms of how many requirements are covered. So what are the evaluations that I have done for this coverage? All this will be part of the test evaluation class. Similarly, technology also we are going to evaluate. That means, for example, I am going to qualify tool also. Example, if you take automotive or aerospace, because we need to uh, subjectively understand whether the tool is producing the right results, the intended results. There should not have any errors. The tool should be error free. All this will be part of this technology evaluation or a tool evaluation. It could be automatic or manual. It could be online or offline with the help of the vendor, whoever has produced the technology or the tool output. So that is about the model based testing classes, categories and options which are used in the industry. Okay, so that is the end of this session where we have described about models and the tasks of the models, model based software testing. Example, taking a calculator, what are the different states it will enter, and when we have the complexity, we define the paths that models can take, and we replicate that using a model separately, as I explained. So that is the philosophy of model based testing, and we list out the features versus its test scenarios categorized in the model based testing, and we can have a classes defined for model based testing in terms of a model, the model where the model is a category, and test generation, test execution, test evaluation, or the other classes. With the help of all this, the model-based testing is carried out. Coming to the embedded system words that we have gone through, embedded system testing words so far in all the units: test harness, test bed, test bench, automated test equipments, model-based testing, which we have studied today and the previous class. Test steps, test drivers, we can probably study in detail in the next classes. Fault injections, MCDC, test hooks, boot software, boot loader, interface control document, breakpoint, simulators, emulators, trace, profilers or profile, datasheet, data, in-circuit emulator, test equipment, code checker, static analysis. I think static analysis, code checking and all that will be part of the next future sessions. And in terms of embedded system jargons, we need to embedded system testing jargons. We need to understand dynamic analysis, X, disassembly, reverse engineering, life cycle, baseline, V model. All we have studied. I will not go one by one. The software integration test, hardware software integration test, IVNV, robustness, normal, nominal, average, states, transitioning, likewise. Okay, some more glossary we studied today. Equivalence class we have studied in separate class. A portion of the component's input or output domains for which the component's behavior is assumed to be the same from the component specification. Error, a human action that produces an incorrect result. Evaluation, the reviewing and inspecting of the various intermediate products and the process of the system under test or development. Expected result, we know that it is a behavioral prediction of the specification for a particular input under specific conditions. Failure, a deviation from the system from expected behavior or service. Fault, a manifestation of an error in the software. A fault, if encountered, may cause a fail. It is a result of an error basically. Functional requirement, required functionality or the behavior of the system. Function specification is a document basically that describes the characteristics of the product with regard to its intended capability. High level testing, we know as a complete product we are going to test it with the help of high level requirements or specification. Hardware in loop, where we put the test with the actual target or the real hardware is used in terms of the testing. And initial situation is one condition, the state which a system must be in the start of the test case. That means a precondition is also called as. It's very important term. This is usually described in terms of the values of relevant input data and internal variables. Okay, so that is the end of this session of the embedded system testing unit 2. So in the next session we will study about the